Ladies and gentlemen, it's a little bit more than 9 o'clock, and I think it's time for us to start. We have a very full program today, and before I introduce the first keynote speaker, I will say a few words about the program so that you're aware about this. Well, we will start with our two keynote speakers first. There will be a coffee break, and then we're splitting up into 3 different panels. And I just want you to observe where one panel is going to stay here, which is the one on health and welfare. And the climate and environment panel will go to Gallery Åbom. And also the materials and molecules will go to Gallery Davidsson, so that you're aware of that. And then there will be lunch, and then there will be the kind of summing up later on. So let me now introduce Professor Cristian Alba Simoniescu. Cristian, you were able to say a few things about yourself yesterday, but I will still add some things. Cristian is professor at the National Center for Scientific Research, the CNRS, and director of the French Neutron Large-Scale Facility, the Laboratoire Lyon-Brillouin. I have learned the pronunciation from you. Since 2009. Prior to that, you were deputy director of the Physical Chemistry Laboratory at the Paris Sud University at Orsay, coordinating a research group on experimental and statistical thermodynamics of soft condensed matter. Your background is in chemical physics and thermodynamics, and you obtained your PhD at the Pierre and Marie Curie University in 1984. You later moved on to Purdue University in the United States as postdoctoral fellow, where you started to work on particular materials, gases, and liquids. Your research topics focus on the thermodynamic structure and dynamics of condensed phases, in the aim of extracting a molecular description of their macroscopic properties. Several experimental techniques are combined in order to bridge the gap between time and space scales, improve theoretical concepts and analytical modeling with a strong contribution of neutron scattering methods. And you all realize that I didn't understand a word of that. But with your help, I would I would probably do so. And the last thing I would like to say is to thank you again for the very valuable and interesting visit that we had at your laboratory. And we are, in this case, the Council on Research Infrastructures in Sweden. So please join me in welcoming
Thank you.
Cristian.
So, thank you very much for your introduction, and thank you very much for your invitation. I'm quite happy to be there today. And we'll start with the speak about neutron scattering. And of course, I'm quite happy since France supports the ESS project at the last steering committee in October, and so we are partner now in this adventure, and this is something I hope that we will succeed in doing it. And before that, we have also a French and Swedish agreement, and Johan Holmberg and Lars Borgersen helped them on this agreement, and they are coming to this place here. And just switch this, yes. And so the lab is we are producing neutron with a reactor here, and the lab is in the southwest of Paris, in a place that's called Saclay. And the aim here is to have the largest French university, Paris-Saclay, next year, starting next year. And you will have something like 65,000 people and student with engineer school. Here is the French Synchrotron Soleil, and Soleil is collaborating a lot also with Max IV. So all these places are quite close to Paris, and now in Lund, very close to work together. So I will give, I will not too much speak about the future, but now about the daily life and today with the materials and molecules examples that I will give you. But I would like to start with some context and some definition, and of course introduce a bit the neutron scattering processes. And then after that, progressively, I will present you some example where the complicity is increasing, and explaining why and how we are building these materials and how he could help in, okay, it's better, and how he could help to at least contribute to the societal challenges. So this is, I try to stuck with a Nordic, so we are habits, so we are all living in IKEA living rooms. I mean, this is something that we all have. I took it from the web, and that I just added my own contribution to this living room. And you see that around you, you have a lot of materials. You can have a painting for your walls. You can have window glasses. You can have bronze, as we saw yesterday. And of course, this is from Rodin. You can have stones. You have clays. You can have your computer, your cat with its litter. You have food, of course, wine, of course, and plants. And all the things are made also of nanocomposite. And this is not an exhaustive list, but this is something that is around you and that makes your life more comfortable. And this is where we are entering. So the topics and the keywords for scientists could be material science, engineering, metallurgy, crystallography, archaeology, nanoscience, spintronic, nanocomposite, soft matter, porous materials, food science, agriculture, whatever. All these fields can treat the problem at its way, and they are addressing the question quite differently. But at the end, the way they are using neutron scattering or the tools are in common. And of course, the aim is to do fundamental and applied research, and there is no really boundary between the two. So what is a material? Material is something which is made of several chemical substances. It's a composition of this. It could be really complex. I don't know, it moves all the time. I'm sorry. And usually to define a material, you associate it to a specific property. This is how you recognize it. Materials could be natural, like the rubber, for instance, or wood. Materials could be also purely artificial and synthesized and manufactured in the lab or in an industry after. This is like your window glass, your steels, your hard disks, or whatever. And for all of them, from the process to making them, and from this chemical definition to the properties that you are, or the final products, all this strategy to get there is called material science. So why neutrons? Just a small, I'm sure you heard that many, many times. Just to remind you why we're using neutrons. Because neutrons are neutrals, there is no charge on it. Neutrons are non-destructive and can penetrate deeply in the materials, in a system, so that's ideal for a lot of studies. Neutrons also is a unique probe who can explore in space and in time at the same time, and there is no equivalent probe so far able to do that. Neutrons is very precise and sensitive and selective for the atoms, and in particular, neutrons are very sensitive to light atoms like hydrogens. And of course, there is then a lot of application for bioengineering, but also for energy storage or hydrogen storage here. And to the end, neutrons has also a small spin. Neutrons is like a small magnet. So I extract these pictures from yesterday. This is the SPAC shot piece that I added because I found it very, very nice. And it looks like exactly a small magnet. And this is really useful for anything related to spintronics, for instance, anything related to supra-high TC, which is, of course, deep physics But it's also very useful for all your surrounding, for memory storage and hard disks that you are using, and that's your life to do your to work with the infrastructures and so on. It might help to have a better access to the properties of the materials. Okay. Okay, but just turn around. So. But I can do this if you prefer. Okay.
If you put it on your head, it's going to follow the mouth. It's much better selection.
Okay. But they told me to put like this. You know, I'm just doing what people tell me. No. I will take this things.
Okay.
I can take these things. Okay. So, does it work? Yes, it works. Good. So, starting with some definition. So we heard about yesterday from Barbara that people are working at the CERN. So I'm not looking anything in the nucleus and how it is made, but I'm starting with an atom. And when you are making atoms together, you are then forming molecules. Some atoms can be just single and exist by themselves, and this is making elements. And when you have a molecule, you are happy to look at its shape and how it is constituted. And you see that by X-ray and by neutrons, you do not have exactly the same definition of the materials, and you can see the atom differently. So the two of them are bringing complementary analysis. And you can increase the complexity and have very big materials and macromolecules. And here it's just an example of a polymer. Polymer makes all your plastics and the things that you have around you. So to associate these molecules and these atoms, that you need a glue, and this glue is called intermolecular forces. And then you can go from something perfectly ordered, like a solid, to something which is less ordered, that's a liquid, or something completely dispersed, which is your gas. And the advantage of the neutrons is that the energy of the neutron is exactly on the scale of the energy that's in between these molecules, and the wavelength of the neutrons is also on the scale of the distance between these two atoms. So that's why it makes it very easy. A good example of glue system is water, and I will speak a bit of water and its consequences around us. And water is still a mystery to understand how it works and how it is associated and which kind of phases are coming out. And especially it's not yet completely understood how water is existing in the liquid state and how it is forming these beautiful crystals in the nature that you have around you. Water can have a great importance for materials, especially at the interfaces. And here it's an example of a fracture. And it's important to see how the corrosion will affect your fracture here, and how after that your fractures will slowly increase and completely break your windows in your car, for instance. And this type of work can be done by neutron scattering, by following how much water was entering just inside here of the fracture. So we did reflectivity here. This is Elisabeth Bouchot who did it. And by reflectivity, you can just follow at the entrance of the fracture how water is penetrating, and then how it could damage your windows on it. So these are direct application on it, but also fundamental questions, because you can extract a lot of laws that are quite universal on the fractures. The second example of water at interface is something that we can observe in the nature for a while. It was already observed, I think, by Pliny the Elder before, I don't know, more than 2,000 years ago. And he found very surprising to see a droplet of water just staying on the water lily leaves. But you can observe it here in your garden as well. And the water is not waiting about that. It's just not waiting, because this surface here or this surface here, which is more artificial, are completely hydrophobic. So they are repulsive with water, they are pushing out. And if you continue this analysis, and this is a lot of work done by my colleague Kere at the ESPCI, you can even follow how a droplet of water is crushed on the solid, which is hydrophobic, and then just because of the repulsion, it contracts again, and it's formed again another droplet. It increases in size, and he will jump above, and after it will come back again. So this is directly something that you can even do at home to follow how a droplet of water every millisecond time here is just crushing and bonding after that on this surface. And of course, the application is directly for you if you want to avoid any water on your windows. Another nice example of even larger molecules is a self-healing project. And this is done by Ludwig Leibler. I forgot, yes, his name is here. And just playing with this interaction between molecules and how you will orient this interaction between the molecules, you can form a rubber, an elastic that you have on your hand. You can cut it, so you have two pieces, and then you put the two pieces in front of each other, and you wait 10 minutes, just like this, and you have your rubber again in a good shape. So you have a without adding anything, no temperature, no chemicals, nothing, and then instantaneously you have once again the same materials. And this comes exactly from this interaction that you have here. So of course, it was a challenge to form it, but it is also a nice materials to have. It means if you cut your shoes or your running shoes, imagine you can just put your two pieces together and then you can use it again. Of course, it's not good for the economy because you will use always the same materials, but I mean, it's also good for other purposes. And the same group of Leibler then developed other materials by combining them and making just with plastics and natural materials like this, almost a window glass, I mean something as strong as the windows that you have here, which is made of silica. So if you increase of course, the complexity, you can mix the molecules, you can have multi-component system, and for instance, water likes to be attached to alcohol, or water is also jumping or moving around proteins, and then you have all the bioengineering and everything where water is always mixed together. And then you can use the advantage of another type of molecules, of very large molecules called surfactant, which is surface active agent. And these molecules have the advantage to have a part which like very much water, which is highly hydrophilic, and a part which hates completely water, which is highly hydrophobic. And when you combine these materials with with an oil, for instance, you are then forming a lot of new, many materials with different sizes and then different properties and different purpose. And then you can go from cylinders to having compact cylinders just by changing the concentration of this surfactant, the water, and the oil that you are mixing in. And then you have lamellar structures. You can inverse your system from here to here. You can play a lot with all these materials here, and that has a lot of consequences. I will skip this. And these consequences is called everything that you can do for soft matter, and this is a soft matter in your daily life. It's your shampoo, it's the way the petroleum is carried out, it's the plastics that you have here, it's a tire that you have here, the ice cream, the painting, and everything, and all the nanocomposite that you can use in your airplane. So this is exactly where it's come from. So a materials is not only that, a materials is originally defined by a structure, and the structure usually is very well organized, and this organization is most of the time periodic. It's very close to a crystalline solid. But of course, to get the materials, you have first to synthesize it, or it can be extracted from the nature, then you have to characterize it to see what is its shape, what is its properties, how it changed was under various constraints, like the temperature around you, or the humidity around you. But an important aspect to become a materials and not simply a solid is to shape it. And just to shape it in order to help it to express as best as possible the properties that it has. And this is quite important now with everything called nanoscience and nanotechnologies, because this is how you are making these fibers, these thin films of everything, or the nanoparticles that you are including in different things, or for instance, I'm sure you heard about nanocarbons and the carbon nanotubes. And all the things come from the fact that you have, one of your wish is really to shape and to provide a given form of your materials. And then of course, you are revealing new properties, because just imagine that instead of having a robust piece, you have something where you have more atoms at the surface that you have inside. So you have to reconsider completely the properties and the mechanism that is developing inside of these materials. So, and of course, you can use these materials as a gas host system. And a good example, what was a discovery from one of your previous scientists, Kronstedt, and this is the Swedish mineralogist, and he not only discovered nickel, but it's something that he discovered. He introduced the word of zeolites, almost 2 centuries ago, and this is the zeolites. This is the kit liters that you are using at home for your cat, and he just, and this is an average structure of zeolite, he just considered that he observed that these stones was, by heating it, able to put a lot of steam out. It means that a lot of water was then contained inside of these stones. That's the origin of the name, of the Greek name of zeolites. It means that water was inside all these cages, and when he was heating it, all the steam was coming out. So since that time, zeolites are a lot used, and then you have all these nanomaterials, and you have definition of length scale of these materials depending on the size on the hole that you have here. So it could be microscopic materials where you have something which is less than 2 nanometers. It could be mesoscopic, and the mesoporous materials or macroporous materials like, alumina or other systems that you can find in the nature as well. And since the 80s, a lot of materials were proposed in the literature and developed, and you see the shapes, the properties, the resistance to electric field, magnetic field, temperature, whatever changes from one material to another one. And I will just give you an example of one of the last ones that came out, which is called MOF. MOF is for organometallic microporous materials. And this is just a combination of something that was metallic, and it is organized like this, with a double pyramidal structure where you have 6 oxygen here and the metal inside. And if you combine it with an organic molecule very close to the one I showed you at the beginning, then this molecule is making the link here between these pieces here at the bottom, and then you have a big hole inside. And then it could be larger, and then you can play either with the metals or either with the organic shape to form whatever you wish on it. And this is called the MOF. And this is very interesting systems, because this MOF, for instance, this is one of the first one. It's called meal, because usually when you have a material, the names are quite... they do not follow the chemical definition, but it's come from the places where it was discovered. For one, you have Mobile in his name. The other one has Santa Barbara SB for its definition. And here you have Mille, because this is Institut Lavoisier. It is the Institute of Ferré who work on these things. So there is no but it's impossible to discover it just by chemical definition. And what is very interesting is that inside of these materials here, you can have a bit of water that is entering here at a very, very, very teeny volume inside. But when you heat it, then the size of the materials increase, so it's just something which is crushed and opening like this, and you can increase the internal volume by something like 40%. This is the largest increase of volumes that you can make inside of materials like this. And this is also, of course, followed by neutron scattering. But what is also important to see with these materials is that you can confine in it something like 400 times the equivalent volume of carbon dioxide. So it's a tremendous application that is coming out with these materials. And to continue in the complexity in the scale, I just added this example of cork. This is cork of bottle of wine, and this is corks coming from the Burgundy area. And I'm using it because this is the first picture we've got with our imaging station at the lab, and this is thanks to the agreements that we have with Sweden, and I presented it already to Lars Borgersen on Monday. But this is, you can follow exactly the level of compression of your cork inside of your bottle, or you can follow also how much it is degraded slide by slide, and how much water is coming in, or how much free space is in from the top to the bottom, inversely, and make this free space allow the oxygens to go across and to oxidize the wine that you have inside. So there is a lot of need to understand how this cork is working and how they are sensitive to water and to oxygen inside. Finally, you can find materials, you have another type of materials where instead of increasing the complexity, changing the molecules and so on, you just think, okay, I have with this material specific properties, I have this with this one, another properties, what it will happen if I'm mixing them together. And this is exactly what condensed hard matter physics is doing, and one of the topics that is really well suited by neutron scattering as, of course, multiferroics, or anything where you are combining electrical properties to magnetic properties. So I just give you here some examples, not an exhaustive one as I told you, but you can form this multiferroid materials are quite studied by now, especially over these last 2 years. And this is quite interesting if you want to make new design for materials that could propagate the propagate the information, making fibers, making sensors, for instance. You can have, of course, molecular magnets. It means instead of having your own magnet here, you use the molecules inside to detect something. And you have other, there is a lot of systems that are coming out. I will not too much enter into the details. Of course, one of the main topics will be from fundamental point of view, will be to understand supra-ITC and to, from the understanding of supra-ITC, being able to propose new materials to have a higher temperature of TC for supra-ITC to go closer and closer to the room temperature where we are working compared to what we have now. An important and practical aspect with all these materials is to work with spintronics. Spintronics come from the fact that you have you are working around the properties of the electrons here. I didn't put the same plot here because now I'm speaking about an electron. And usually when you are playing with a charge of this electron, you are speaking about electronics. But if you consider that your electrons have also a spin, then, a small magnet, then you can build the discipline which is spintronics, and then you can use the studies to write, store, and read any information that you might need for your computer. So it's very simple. You just have to build blocks one over the other one and look how the properties and or the information are commuting from one layer to another one. It is exactly like a Lego layer here. And this is This is quite important because with this, when you are building something like this, it's not simply the sum of the properties of the platinum or the copper or whatever. It's just you are making something new, and it's not simply this sum, because then new properties are coming out that you cannot completely predict in advance. And this is this increased complexity, which is important to understand and to see that by simply, if you have chrome here, if you have manganese here, and if you have another slide of chrome, what you are proposing here is not simply the materials that just the sandwich materials, and you are expecting something simple. You are really producing something new in terms of magnetism. And I just remind you that the first application of spintronics comes from the discovery of the giant magnetoresistance. I mean, something like how much it makes, more than 25 years ago. And the Nobel Prize came for Fert and Grünberg in 2007. But the first application came very, very fast. I mean, only 6 years after. And this application was on the sensors for the brakes. And it was applied by Mercedes. And testing it for sensor for ABS brakes on their wheels. And now after that, even a bit later, there was used also for data storage. Quite recently, but to go from the discovery here, which in '88, to the application here, the time was very short, but it's really an exceptional example where you can go from something that was so, abrupt to understand, and even the word what is giant magnetoresistance, to go to something which is so easy to understand now, which is data storage for your hard disk that you are using. And 6 years is not so much, it's very, very short. And usually it's more than that between the discovery and the application for industry. But it may happen that it can be also very short like this. So we never know when we are doing your research how far and how fast it will go to the application here. So a good, and the last example of materials are of course related to metallurgy. Metallurgy, you are using it all the time in your house, when you are traveling, in the train, in any tools that you are using. And I will just give you 2 examples that are very where neutrons are very, very useful. When you are analyzing the crystallographic structure of a metal, which is made of different components on it, you have different small crystallite inside of your materials, and you can look at them by neutron scattering and do this analysis of textures that you are speaking now. And for instance, if you look at your golf here, and you can see how the metals are organized inside. If your metal is well aligned like this, I mean, one of the consequences, I'm not practicing golf, this is, I just believe, then apparently if all the metals is organized on that way, then usually you are making a good shot with your golf gun. But if it's organized like this, and you see lines that are breaking together, then the heat is not as good as it should be. So this is a direct consequence of the studies. Another good example is how much stress you might have. So this is inside of our guide hole in the lab, and you have a big element coming from an airplane here. So you have to analyze what is the stress inside, because you always have, when you are building it, you always have residual stress between part of your system. And if you have too much residual stress in one of the elements, you can break it, and it cannot resist to effort when you were using it. So this is also quite important, and you can have big wheels coming from trains, or you can have this part coming from airplanes and other military applications that I'm not allowed to speak about here. But it could be also useful for archaeology, and this is another example, still metallurgy, but prehistoric axes where they were studying the. This come from graves from Lombardy in Italy, and from these graves they find axes, and depending on the position on the study where they look at the composition of this axis around this axis here, they find that some parts were already they could extract how it was formed and which kind of manufacture that was using at that time due to the constraint, as residual constraints that was appearing here. And they could also explain and even put a datation of the on the evolution and how the materials was evolving with time. Still, this is still doing metallurgy, and this is an ancient Greek lamp, and this is for Dimitri. And you see that what was studied at SNS, at Oak Ridge. And you can also, by neutron imaging, go across the materials, because I told you this is very, very penetrating. And when you have something old like this, which is completely closed, it's difficult to open it, and because you can destroy something by doing it. So the first step is to look across of it, and this is exactly what neutrons can do. And then, of course, the question is, where is the genie? What is inside? Last applications come from PSI, because there is a lot of work done on neutron imaging, and this is really the leader center now in Switzerland for this type of analysis. Come from that can tell you how plants are evolving in a given soil, and then you can see how the roots are to go across this. So you have your plants here and you have your soil inside, and to see with time how your roots are evolving, what is the impact of a bad environment of the soil, what will be the impact of metals in the soils, how water was penetrating your roots, how these roots will be developed. There is only neutron scattering can go and look across of that, and this is the type of pictures that you can extract. So I'm finishing. And so I try to show you that there is molecules and materials, there is a lot of things. And I didn't give you here any exhaustive, of course, list. And there's so many domains where you find materials and where you need molecules that, this is really the basic of anything that you can build. You can go from the atomic scale, and you can go from something which is at the angstrom size to something that makes meters. And you can just, by doing it, in fact, by doing it, you are just increasing the level of organization. But each step you are increasing this level of organization. In fact, you increase the complexity, and you have to introduce new concept on it. So you have each time to work on it, and it's nothing is completely determined by the first fundamental rules. It's not because you will know, and I have nothing against CERN, but it's not because you will know about the Higgs, the Higgs boson, that you will understand what is happening in your soil and in your roots there. And you have really each time some scientific area and the need of research at all this level to understand the new concept around you. And this is exactly what neutron scattering is offering. And of course, the nice combination of ESS and Maxwell could be very helpful for that. And for illustrate this increase of complexity and how much you have to develop new concepts step by step, I just want to refer to this paper from Phil Anderson, who was Nobel Prize, and explaining that more is different. More you're adding complexity, more you're adding materials, more you have something different at the end. Thank you.
Well, thank you very much, Christian, for a very interesting and pedagogical, I think, presentation of the of materials and molecules, and also the usefulness of neutron scattering. I think that was absolutely clear from your presentation. We will have to go on very soon with the next speaker, but I just want to give maybe one, if there is a question to Christian on something here. So you're willing to, you're able to put a question. Or maybe we can talk to you later, right? Okay, well, thank you very much again. And our next speaker is Mats Melby.
And my slides.
Mats is a professor of epidemiology and executive vice president of Statens Serum Institute, SSI, in Denmark. He's also director of the Division of Health Surveillance and Research at SSI. He has held research positions in epidemiology in Denmark and at the National Cancer Institute at the NIH in the United States before he became state epidemiologist and later professor and head of the Department of Epidemiology Research at SSI. Over the years, Mats has been involved in a large number of Nordic initiatives, for example, the Nordic Biobank Initiative, the organization of a Nordic summer school on infectious disease epidemiology, and he has been the chairman of the board of the Nordic Medical Research Council. He has extensive experience in research within epidemiology and has been a key person in forming the Danish system making biobanks and registers available for science. And Mats will give an overview of the Danish organization of registers and biobanks, and I think we all envy your system. And he will give his vision of how this could inspire the future building of joint Nordic infrastructure in these research areas. So please come to the podium, Mats. Thank you.
Oh, and thank you very much for the invitation. I'm very, very pleased to be here. Get some slides up here. Okay, so I will this morning talk about a new creation in Denmark. We have actually changed our way of looking at the health data, or in particular the way we organize them. And I think that could actually be a stimulation for you to actually learn about the system. I think we have a chance to actually bring more Nordic collaboration together by using this kind of a system. Now, we have all in the Nordic a PIN number. We don't have exactly what we have in Denmark, all of us, but we certainly have the PIN number by which a lot of the different registry systems are linked. This picture illustrates what's happening in Denmark. We got the CPR number in 1968 and has since then linked a lot of different characteristics of the Danish population by this CPR number. So we can follow the individual through several generations, actually 4 generations by now. We can study the individual from birth to grave. We study millions of individuals, and therefore when we come out with research results, they are normally very robust. All this has not been done for research, but actually to create the Nordic society model, you can say. But it's very cheap to turn that around and make use of all this data for research purposes. And I think that's a very important issue. We have an ethical commitment or obligation, I should say, to actually make use of all this data. So we can sit behind the computer and study the individual from birth to grave. We can, for instance, study a pharmacologic drug that has been put on the market by a company to treat a particular disease. But this drug may also have other effects that the company not necessarily study. As researchers, we can study what happens 10, 20 years down the road having been treated with this drug, whether it's safe or not. We can also study this situation when a person has a disease and then take a drug. Does the drug work the way the company tells us it should work? This is so that maybe only some people react to this drug and get healthy, whereas others don't. And if that's the case, we might be interested in studying that issue. And we can do that now with a lot of the different biobanks that have been developed in the Nordic, because they actually tell us what's happening exactly in that individual at particularly that time point. So those blood specimens actually give us information about the genetic structure. The genetic structure in itself is not the most important issue here. And I think when we have the ethical debates about genes and how we actually handle, genetic information, I think that we are actually behind. The genes we have are more or less the genes the pig has. So who cares? Really what matters is what is functional. Why is it that the mouse has genes that actually are active for vision and hearing? That's survival kits for that mouse. But we have other genes active. And that's where it comes into the aspects of functionality. I think that's much more important for us to actually look at and address than what kind of genetic composition we have. Now in Denmark, we had a lot of the different information from the healthcare system lying in different institutions over the years. But the chairman or the director of the Ministry of Health decided overnight, more or less, that he wanted to change this. So he said, we need to pull it all into one institution. So there's only one place where we have this, where they can take care of it. They handle it in the same way, irrespective of what kind of information it is. And then, of course, they also have the obligation to give out the data to the society again. And I'll come back to that. So one institution. And you have to look at this as we only take a copy of all the data out there. We don't take the data. So the data are still out there in the regions, in the municipalities, at the hospitals. But the government, the official Denmark, takes a copy of all that data into one institution. That institution is the State Serum Institute where I'm placed. And we also now have all the economical data attached to that. So if you get a surgery for appendectomy or appendicitis, for instance, I know exactly what hospital you went to and had that procedure taken, because we have to pay that hospital for that procedure. So by having all that data, we transfer something like 20 billion kroner a year just by documenting what happens out there. And on top of that, we have created the Danish National Biobank at the same institute. So we have all the dry data and all the wet data in one institution. Now, that gives us the responsibility to make sure that everyone outside of that institution also are happy and get all the data back. So we have created not only a view of how we enter data, one entrance, but we also want one way out of data, so that people don't have to look into different web pages or whatever to find data. So we could create a web platform which is called eSundhed.dk. And if you go into that, you can get the data out you need. If you are a ministry or region that runs the hospitals, they can immediately go in and see how do we do right now. Or the municipalities, or even the citizen. We have a system called Health Quality, translated into English, where the citizen can go in and look up what hospital performs the best exactly for my problem. And we'll change that so the individual in the future next year can actually play with it and say, I want a hospital that's small, clean, with nice-looking doctors, or maybe even some who can treat patients. But they can decide themselves. It's really an individual way. They will be able to play with this in the future. And then finally, we have something else which is not under my responsibility, which is called Your Health Record. The individual can go in on this page and look up all the procedures that have been given to me. So that's actually my file, kind of. Only I can access that. This spring we got a new reform that actually also will change the system in Denmark, which is called the transparency reform. In the old days, we actually, when we went to the hospital and had a procedure done, for instance, removal of the uterus, you would be in hospital for 11 days. Today you are in hospital for 24 hours and then you're out. So the rest of that treatment is taken care out at the GP level. We don't know enough about what's happening out there, and the government wants more details about what happens out there, because we want to study the entire period from starting out with having a problem as a patient and then ending at the other end, getting back to into work again, to the labor market. Or put this way, it's okay that you actually do the surgery, but I mean, if the patient doesn't get back to the labor market again quickly, you might actually consider doing it in a different way. So the focus will now be from more activity to right activity. What's the right procedure to make sure that the patient doesn't get back to the hospital a week later? And we also want to be inspired by the good example, so best practice. So daily activities should be based on active use of data and documentation much more than today. And we actually want to study the best practice throughout, all phases of a patient regime. The best healthcare that the money we have can give us. And I apologize for this being a Danish slide, but I think that most of you can read it. You remember one of my first slides where we took the course from birth to grave, and that's the way a lot of us have worked for a long time. This will really change things a lot, because if we can also have very detailed information on the entire course of the patient from his first diagnosis until he's back in work, we can change a lot and make things better. Which means we need to have much more information on what's happening at the GP level, but also in related areas around this patient. So we're building that out in great detail in Denmark right now. Now, I showed you the page where you can get in and get data out. But in addition to that, we have a web page or a situation for a researcher where he can go in and play with the data in much more detail than anyone else. And that was just created. It's a Citrix solution where the individual researcher can actually get access to all the data we have. So imagine that we have behind this wall all the healthcare data. You then get permission to go behind the wall. You are certified first. There's a procedure there, but when you have been certified, you can go behind the wall. And then you can pick whatever data you like to work with and put it up in a file. And then before you can work and really analyze the data, you have to go through the procedures, getting the permissions from the Data Protection Board. But that's all. You just have to follow the law. Then you can start working in a few days, 4 or 5 days later, in that file, on your product. And if you want more data, you can go back and pick them and put them into the file for more days. You have the permission, you can go on again. In the old days, we had to actually apply. It took a long time before we got the data out. And then when we had analyzed for some time, we discovered we needed more data, but we didn't want really to go through the whole procedure, asking permissions and all that to get more data. So we published with what I would say, not the optimal design always. And I want the best research conditions. So this is, I think, a unique way to make sure that we get the most out of the data that we have. So research can themselves put together the data set they need behind this wall. Then they can also, if they want to do a clinical trial, they can put it together behind the wall and then apply to get the data out with PIN number. So they can do a clinical trial, or they can actually look into the files whether the diagnoses that they are working with are correct or not, or they can link up to a biobank. For that, they also need the PIN number. So you can get the data out again. Not total copies of registries, but a particular data set for a study that is, for instance, a clinical trial. You can also put other data behind up that you have collected yourself behind this wall and combine them with data from the healthcare system. So we focus that way on data security and at the same time flexibility for the researcher. Now, behind this wall you can play with all this data. And that's a lot. And right here it says lab results, and I'm fascinated with this because while I'm speaking right now, we're building this new facility up. So we are taking a copy of all lab results for the entire country of Denmark, immunological data, biochemical data, whatever data you can think of. We'll get 500,000 new data points in every day in the future. So can you imagine that we have a measurement on all the cholesterol measurements of Danish citizens in this what's called a registry. Then we also know who eats statins. That's a drug that can actually change your cholesterol level. And you can then follow up, having taken the statins, does this treatment work? Does the cholesterol level really go down or stays up? And then as a researcher, you can say, I want to study those that really respond to statins. So I take 1,000 of those, and those that don't respond to statins, and I take 1,000 of those. And then I go to the biobank, and I study why some respond to statins or not. This system is marvelous because you can actually take one drug after the other and study personalized medicine. For whom does this medicine work, and for who doesn't it work? And I think, and I know I'm dreaming a little, but I'm still provoking the other Nordic countries to come in here and play with us. Because if you decided in the same way to put all your healthcare data in one institution, just a copy of it, so you don't have all the trouble getting through all the different organizations, getting all the different permissions, then you might be able to build a similar wall. And can you imagine then, being a Nordic researcher, you could define your data set behind this wall in your own country, then submit it to the file in the Nordic cloud, and then analyze a combined Nordic pseudo-anonymized data set, or even an anonymized data set, behind a Nordic wall. I know there are clever people in the Nordic that can design this. This is really just the political will to do this that we lack. And we could then work not with 5.5 million, but more than 25 million in this. Now, another thing I'll touch on is the Nordic Biobank Initiative, because this is probably, certainly the way I look at it, a master example of Nordic collaboration. We have had extremely help from interacting in the Nordic, building these new infrastructures. They cost a lot of money, but having had all these meetings supported by Nordforsk, we have been able to learn from each other and making, I hope, the right decisions in what we buy. We have even pushed down the price from the companies because they knew that we were talking together. So we've got very good prices on our equipment. Moving forward, at the same time building these systems. We've also had a lot of how to do seminars and exchange of information. So I really look at this as one of the success stories of Nordforsk and Nordic collaboration. You may know that, or not, but at least the different governments in the Nordic have at least, by now, put 1.5 billion kroner into national registry systems, and maybe even 2. So we really have built some nice infrastructures all over the Nordic. I will touch a little on what is done in Denmark with respect to the biobanking, in particular a registry system that we have built and that I think could be really transferred into a Nordic registry model. So in Denmark we have something called the National Biobank DK, which is a system that builds on 3 legs. A physical biobank at my institution, which now includes a blood specimen on more than 3 million Danes out of 5.5, 6 million specimens. We have a registry system where we combine all the large registries or large biobanks around Denmark. They only send in to us the PIN number of the person behind the sample, what it is, blood, whatever, saliva, whatever, when it was taken and what temperature it has been kept at. Then here at my institution we link it up, so the person behind that blood specimen, we link up to what happened to him later on. So if the specimen was collected in 1999, he may develop prostate cancer in 2007. So we have this specimen 8 years before he developed this cancer. We put that information on the internet, not person identifiable, but as anonymous data. And I'll show you how that works. You go into the National Biobank DK homepage, you press the biobank register, and you get into this page. You can, if you're a researcher, you want to do a study on, say, multiple sclerosis. You want 400 patients with a biospecimen taken only among females, only that period. And the mom and dad have to be Danes or Swedes or whatever. Then you can say up here, country of birth of patient, mother, father, year of birth, and so on. You can go to diagnosis. And here you can work with ICD-10 diagnosis. That's the way doctors work. I mean, we have classifications for diseases. They are called ICD systems here, ICD-10. You can work with ICD-8, SNOMED codes, and so forth. You can even, the SNOMED, you can work with morphology and topography. That gets very detailed now, but then you can put in here, now this is not multiple sclerosis, I'm afraid. This is depression, but I mean, you could put multiple sclerosis in. Depression is put in here, and then you get all the ICD codes out here. You can pick those that you want. They go down here. That was for the ICD-8 system, and the ICD-10 you could do the same. And then you go forth to the sample here. You can say, I want specimens from all the banks or only some of them. Pay attention to here, Genetic Biobank of the Faroe Islands. So we have actually got the Faroe Islands into this system now, and we're trying to push large biobanks around the Nordic to actually join this. So we hope to make it Nordic one day. And here, the blood, if it's barcode, serum, plasma, whatever, tissues, biopsy, large specimen, bone marrow, fine needle aspiration, other type DNA, and so forth. You can choose whatever you need. And then you go to report definition and say, you can do an X by Y. So you can ask a lot of different questions this way. This is country of birth of the patient and gender, we ask. And here we ask number of samples, but you could also ask number of individuals with a biospecimen. And this, I think, is fascinating. If you're a cancer researcher and you only want biospecimens taken, that you only want, say if you're a cancer researcher and you want to study biomarkers before cancer development, you of course would be interested in biospecimens taken years before the cancer diagnosis. So here you can ask, you can just put in, I only want to have information on biospecimens taken 5 years before the cancer diagnosis. And then that's what you get out. Then finally you submit it here, put your email address, and out get the output into your email, and the numbers. And here we asked for birthplace and gender. You can see in the Danish Biobank, we had a lot of Swedes, 1,300 females with depression. We have a biospecimen we can study and so forth. But 250,000 Danes. I'll finish by a few examples of how we make use of these resources in Denmark. So, as you may recall, we can study diseases through generations. So you can say we have a black box where you can put in this disease and ask whether it works in families, and out comes the result. And we also have a lot of biospecimens. For instance, the PKU cards, the Guthrie cards, the filter paper, the blood specimen that is taken from the heel of the newborn for all Danes, and it's done also in Sweden, in Norway, and Finland. You have them, but you don't use them. We use them, well, you certainly don't use them to the extent they could be used, I should say. We use them for research purposes. We have a blood specimen for all kids from 0 to 35 years of age. So nearly 2 million kids. So we use these blood specimens here. And this is actually Science that wrote this paper, Science Gold Mine. This is an example, pyloric stenosis. We wanted to study this condition. It's a condition among newborns. They are born healthy, these kids, but in few weeks they develop a very large muscle in the system, from the stomach to the rest of the intestinal systems. I mean, if you go to a workout place, you'll work for many, many weeks, months before you get really big muscles. But these kids develop a very, very thick muscle very quickly. Something very peculiar is taking place. Now, a lot of those died in the old days, but for 100 years we have known that you just cut this muscle and they are healthy. This gives rise to most surgeries among newborns in Denmark. So we put that condition into this black box and ask, does this work in families? And out comes twins. Oh yeah. If you have a sister or brother with this condition, you have a 20 times increased risk yourself. If you have a half-sib, you have a 5 times increased risk, irrespective of you share the uterus or not the uterus, which really makes us think this is genetics. So what we did was to go from here to the biobank, take out 1,000 surgery-confirmed pyloric stenosis cases and 2,000 controls, extracted the DNA, did DIVA analysis, and have found a lot of interesting things that have been published recently in different journals. And I will not go into that, but go to another example, which is the vaccination database we have. So we know exactly who all of the kids in our country are vaccinated, and when and with what product. And we have used that for a lot of different things. And I think one of the famous papers is this one. We have disproved that there is an association between autism and MMR vaccination. But there are tons of this that I don't have time to go into today. But what I will just dwell on is some of these vaccines have side effects, and we all know that. I mean, MMR is a live attenuated vaccine. So some of the kids get fever and febrile seizures. Can we distinguish those from those who don't? That was our question. So again, we went to the biobank, pulled out 1,000 kids with isolated febrile seizures, 1,000 kids with febrile seizures just after MMR vaccination. And we have found astonishing things here that I, again, cannot go into, but really explain some of these mechanisms behind this condition. So in the future, you may be able to say this kid will be at increased risk and then take your precautions, or maybe do something else. Even treat the kid before you do it. Third example, breast cancer research. This is an old slide. A lot of you have seen this before. When I was a young doctor, I learned that you have to have your kids early, and as many as possible as a woman, because then you not only get your kid, you get an extra bonus, you get a reduction in breast cancer risk for the rest of your life. It's not exactly that way. So again, if you take the entire population of Denmark, 1.5 million women in this case, follow them forward in time, we know when they give birth to their kids, we know when they develop breast cancer, some of them, you can study this phenomena which is here. So this is a 20 to 24-year-old woman that has no kids. Now she gets one kid. That reduces her breast cancer risk by 10%. Now she has one and get another one. She gets 10% reduction more. Now she gets a third kid. She gets 10% on top of that. And a fourth kid, certainly 10% or even more. If you wait having your kids when you're up into your 30s, you get your kid and that's nice, but no bonus. Okay? So there's an age interaction here. But really what I think is an interesting question is, what is it that the pregnancy does to reduce breast cancer risk, the most prevalent cancer among women. Can we learn about that? We might actually be able to do something about that. So what I did was I took the entire population of Denmark. I called up Norway. They have a marvelous registry also that we could use. So we put all our resources together, made up a cohort of 107 million person years of follow-up, all women follow-up. Here in Denmark, we know exactly those that have induced abortions, what week they had it. So you have a pregnancy that lasts only 6 weeks, 8 weeks, or 10 weeks, and then it's cut. At the other end, we know exactly when you give birth to your kid, whether it's 40 weeks or 30 weeks, or even younger than that, or earlier than that. So that's the gestational week down here. Having all this, this is insecure, just unstable figures. The confidence limit is above this red line. So what we have learned here, and that is really staggering results, is that this protection takes place in pregnancy from one particular week till the next. And I have read a lot about this. There's nothing in the textbooks explaining what happens exactly between that 1 week and the next. So what we're doing now is we're doing omics profiling, using again the biobank materials, taking women in this gestational week and that one, and studying what is the difference between those 2 weeks. And we are using tens of thousands of analytes doing this. And I'm working intensely with Mike Snyder and his group at Stanford that have developed this IPOP technology, where they work with all kind of omics structures and make really sense out of this. And again, this is not the time for getting into details with this. So, but we hope to, of course, to be able to find out what happens here, and maybe we'll be able to change the situation. The final example is the National Drug Prescription Registry. Now, we have developed this to make sure that chronically ill get a reduction on their medication price. So they put in the prescription here, it's keyed in microseconds here, back to our computer and to the pharmacy here. So she knows that this guy already bought for more than 1,000 kroner medication, so he should have a reduction on the price. That system gives us details about what medication people are given in the entire country. So with that we can do post-licensure studies. Does the drug work exactly the way they tell us it should work? We can study the long-term effects of a particular drug. We can actually study whether a drug on the market also have other implications, so that it works on other diseases. And we have done a lot of studies here. And actually a lot of these studies recently have been done in populations that you cannot study pregnant women and kids. You cannot do clinical trials on those. But we can study them because pregnant women are sick and they do get medication. So we can study those that eat this medication, whether it's safe for the kid later on. So we've done that a lot. And actually the final one that just came out yesterday here has to do with fluoroquinolone, which was actually told to be dangerous and give rise to retinal detachment, which is really a severe condition. We have shown in Denmark this is not true. So you can use all these information to actually do personalized medication in the future by starting a sick population here. Some get healthy from this drug they eat, others don't. You go to the biobank, draw out the specimens, and you may be able to find that there's something in the genes that determines why some respond and others don't. So, concluding remarks here. We really, and this was the Danish example, but we really in the Nordic have an infrastructure that the rest of the world envy us, and we should make use of that. We have an ethical obligation to actually make use of that. So we can really advance personalized medicine for the entire world in the Nordic. We can develop new screening tools by learning what is happening. We can study biomarkers for disease much, much better than anyone else. And we can come to new treatment modules. But we have to do it now. There's a time window of opportunity because the rest of the world out there have actually woken up and found out that it's marvelous to have data. China is collecting data really today. And in a few years, they have so much more data than we could even dream of. They don't have the time scale, the many years behind. I mean, we have had all these registers for many years, but we have to make use of them now. And we also have to actually talk about our legislations. That of course ethics are important, but we also have this ethical obligation to make use of what we have here for the health and prevention of disease and treatment of disease for the rest of the world. Thank you very much.
Well, thank you very, very much, Mats. And I particularly think of your last words, that we have an ethical obligation also to use what we have. And I think let's hope that we can go on and work even more together and use this data. Will you be staying on a little bit for the? Oh, that's very good, because we are running a bit late here on time. We have a coffee break, but we are supposed to start the panels in about 15 minutes. So I think that questions can be asked to you in the panel where you will also be participating. So with those words, there is time for a little time for coffee, and then you will all gather in the different panels in the different rooms. Thank you.